Good afternoon, everyone. I'm Tian Shen. It's a great honor to be here at the 22nd Fibonacci Conference to present our work on multidimensional Zeckendorf decompositions. This work is joined with Jerry Chen, Sebastian, Tian Shen, and Allison under the mentorship of Professor Stephen J. Miller and Dr. Garrett Trash. First, let me begin with the basics. The Fibonacci numbers are defined by the recurrences. Fn plus 1 equals Fn plus Fn minus 1 with F1 equals 1 and F2 equals 2. Now, Zeckendorf theorem proved in 1972 states a beautiful fact that every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. This is done greedily. I'm showing an example. For example, 51 equals 34 plus 13 plus 3 plus 1 equals F8 plus F6 plus F3 plus F1. Now notice that if we get a sum of consecutive Fibonacci numbers, obviously we can use the Fibonacci recurrences. Now, how do we generalize this? We can generalize the Fibonacci sequence to positive linear recurrences sequences, which also called PLRs. Following the definition established in prior work, for a positive coefficient vector c equals c1 dot dot ck in z to k, we define a sequence xn which is contained in z such that x1 equals 1, and for n from 1 to k minus 1, we can get some good initial terms. And for all n is greater than or equal to k, we can use the recursion. Let me show you an example to explain this. Let vector c equals 2, 1, 1, and the initial terms x1 equals 1, and x2 equals 2 times x1 plus 1 equals to 3, and the x3 equals 2 times x2 plus 1 times x1 plus 1 equals to 8. Now we get 1, 3, 8, the initial terms, and for n is greater than 3, we can use the recursion xn equals 2 times xn minus 1 plus xn minus 2 plus xn minus 3. So we get the sequence like this. Now we come to the heart of our work. Anson and Bignell Johnson first extend this notion to a multidimensional setting, z to k minus 1. They gave a definition. First, vector x0 equals to vector 0. And for I is less than k, vector x negative I equals to vector ei, which is basic vectors. And for all the n in z, vector xn equals to ci times vector xn minus 1 plus dot 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 plus ck times vector xn minus k. While we usually move forward, the assumption of ck equals to 1 allows us to define new vectors backwards by the recursion, like this formula. Let me add some explanation about this. From the former definition, we fixed k initial terms, and we can use the recurrences forward to get everything beyond it. Right now, we think about everything before it. So, before ck equals 1, to extend the sequence to all negative indices while keeping integer entries. And that's the most interesting and important ones that guarantee a unique representation. Now, let's talk about the satisfying representation. Before we dive into the general case, let me remind you what the Fibonacci case looks like. Fibonacci, also called PLRS with vector c equals 1, 1, which means they are non-adjacent Fibonacci numbers. And now, what is a vector c satisfying representation for vector v in z to k minus 1? First is the sequence an, which is contained in z plus, and we only consider negative terms. Vector v equals the sum from n equals 1 to n of an times vector x negative n. And it cannot replace terms using the recursion, and all the coefficients are bounded appropriately. For example, let us consider vector c equals 4, 2, 1, and the first example is v1, whose coefficient is 2, 4, 2, 1. So we can use the recursion, which means it is not satisfying. And the second example, vector v2, whose coefficient is 0, 1, 5, 1, 1. Oh, we noticed that the coefficient is number 5, which is bigger than the biggest number we have in our recursion, 41. So it is not satisfying as well. And the third example, vector v3, whose coefficient is 0, 2, 1, 0, 1. So it is a satisfying one. With this definition in place, Anderson and Bignew-Johnson proved the following fundamental result. Every vector v in z to k minus 1 has a unique vector c equals all one satisfying representation. This brings us to our main result. First, let me show you the definition of weakly decreasing. Vector c equals c1 dot dot ck is weakly decreasing if cn is greater than or equal to cn plus 1. And our main result is if vector c equals c1 c2 dot dot ck is weakly decreasing and ck equals 1, every vector v in z to k minus 1 has a unique vector c satisfying representation. In order to prove uniqueness, we use a scalar product map defined by dot product modulo xn, which is bijective. So uniqueness in the scalar case transfers directly to ours. And in order to prove existence, we use what we call the carrying and borrowing game. The question is how to turn a non-satisfying representation into a satisfying one. The idea is simple. First, the borrowing, if a coefficient is too high, decrease it by expanding the recursion. And the carrying, if we have a copy of the recursion, we can absorb or condense it into the previous term. Let me show you an example. Step 0 is the initial state, which means the representation 0, 2, 2. And the first step, we use the borrow. So we minus 1 in the coefficient of vector z2 and add 2, 1, 1 to the backward. And the step 2 is carry. So we absorb 2, 1, 1 to the formal coefficient. And in general, how do we go from non-satisfying to satisfying? Here is the algorithm. Suppose we have a non-satisfying representation. First, we start reading from left to right, and if we complete a copy of the sequence, carry it up. Else, take the first overfilled element and borrow from it. If the result is still non-satisfying, then we repeat it. Finally, if the algorithm terminates, we get a vector c satisfying representation. But does the algorithm always terminate? Unfortunately, the answer is no if it's not weakly decreasing. Let me show you an example. Let vector c equals 1, 3, 8, which is not weakly decreasing, and consider the representation 0, 2. When we do some carry and borrow steps for several steps, we can get the representation 0, 1, 2, 0, 0, 5, 2. And then we continue the algorithm, and eventually we can get the representation 0, 1, 2, 0, 1, 3, 0, 1, 3, 0, 0, 5, 2. The key observation is that the prefix 0, 1, 2, 0 and surface 0, 5, 2 remain fixed, while the middle gains an extra 1, 3, 0, 1, 3, 0 block every cycle. The algorithm will therefore loop forever, inserting more and more terms in the middle without ever terminating. Now back to our main result. If vector c is weakly decreasing and ck equals to 1, then for every vector v in z to k, there is always a representation for which the algorithm terminates. Our main result also inherits some special properties from the scalar PLS case. First, let me show you the central limits type theorem, which is proved in 1952. As n goes to infinity, the distribution of the number of mounts in the Zeckendorf decomposition for m in interval fn to fn plus 1 is Gaussian. And we proved the theorem 3.5 for weakly decreasing vector c with ck equals 1 as n goes to infinity the distribution of number of mounts in the general Zeckendorf representation for vector v in Rn is Gaussian. Here, let me show you some visualizations. First, the definition of Dn represents the set of all vectors in Z2 that can be expressed using only the vector x-1 to vector x-n. For vector c equals 2, 1, 1, which is weakly decreasing, here are the regions from the D1 to D8. We can see the regions expanding outward in a beautiful spiral pattern from the region, and the black point is the vector 0, 0. Here is another observation. Dn is contained in Dn plus 1. For example, D5 is contained in D6, which is contained in D7, and go on. And for vector c equals 1, 3, 8, 1, 3, 1, which is not weakly decreasing, as we saw before, the algorithm may fail to terminate for some representations, so the existence of unique representation for all vectors is not guaranteed. The figures of D1 to D6 also shows that it cannot fill the entire space. The last example is vector c equals 1, 2, 1, which is also not weakly decreasing. But even if it's still not weakly decreasing, it seems to slowly expanding outward in a spiral pattern and eventually encompass all of Z2. This leads us to our further research first question. Which condition on the coefficient vector c characterize when the carrying and borrowing game terminates? And the second question is, how does the expansion rate from the origin depend on the coefficient vector c? Thank you for your attention. I'm happy to answer your questions.